Welcome to the second part of Algorithms Activity Pack. In the previous video, we looked at what is computational thinking, what are the different strands of it, and how algorithm fits in the four strands of computational thinking, and what are the different components of algorithms, and what are the key things that you need to consider when you do it, how can you represent it using flowchart and pseudocode, so on and so forth. In this video, we will look at a couple of key algorithms that are widely used. We will look at first sorting algorithms. There are different sorting algorithms, but we will be looking at two important ones, which is a bubble sort and a merge sort. Why do we need sorting algorithms? It is very essential in this day and age, especially with so much data flowing into any system, that we need to be able to find what we want and sort them in the right order. So, for example, if you look up Amazon and you're looking for a laptop, for example, and you would want to sort them based on the price from lowest to highest, or based on relevance, or based on the brands. So the sorting algorithm helps you to filter out the data and show them in the way that you want them to. Let's talk about bubble sort. What happens in a bubble sort is the larger number bubbles slowly up to the top of the list, just like you would see in the water. So this is one of the simplest algorithms, sorting algorithms that you will ever have. In this algorithm, what we do is we take a list of data. It can be numbers, it can be names, it can be anything, and we compare them so that at the end of every iteration, which we saw in the previous video, the largest number will bubble up to the top of the list. How does it work? Let's look up these numbers 6, 5, 3, 1, 8, 7, 2, and 4. So we first compare the first two numbers, 6 and 5. We check if 6, which is on the left, is it less than 5? If it is, we leave it as is. If it is not, then we swap those two numbers. In this example, 6 is not less than 5, so we swap. And now, because now these two numbers are in the right order, we take 6 and 3. Again, 6 is not less than 3, so we swap. We then move on to 6 and 1. 6 is again less than 1, so we swap. Then we check 6 and 8. 6 is less than 8, so we do not swap, we leave it as is. What happens next is we move on to the 8 and 7. 8 is less than 7. No, so we swap. And then we have 8 and 2. 8 is not less than 2, so we swap. And then we have 8 and 4. We check if 8 is less than 4, it is not, so we swap. Now at the end of this one pass or one iteration of comparisons of numbers, we have got 8 bubbling up to the top of the list and being in its rightful place. So we know at the end of first pass, the largest number is in its right position. So we've got 8 in the right position. We keep doing this until all the numbers are in the right order. So the next time we would compare 5 and 3, we swap. Then we have 5 and 1, we swap. Then we have 5 and 6, we leave 5 as is. Then we have 6 and 7, we leave 6 and 7 as is. We have 7 and 2, we swap. We have 7 and 4, we swap. And the second iteration or the second pass will bubble the number 7 next to 8. Now, we don't have to look at 7 and 8 because we know they are already in the right place. So, we do this process for every single number until we have got all of them in their correct order. So here is an example if you want to have a look. So at the end of the first pass, you will have this number. This will be your second pass, third pass, fourth, fifth, and you will have all the numbers in the right order. Now that is one of the easiest sorting algorithm that you'll ever see. But then it takes a lot of comparisons. It takes a lot of passes. For example, it takes at least a maximum of n minus 1. If you have 8 numbers, it at least takes 7 passes to get all of them in the right order if all of them are in the wrong order to start with. So imagine doing that for around 10,000 numbers or even a million numbers. It's going to take a lot of time and the processing power too. So we move on to merge sort, which employs a divide and conquer technique to do your sorting. It doesn't do the sorting of the whole number step by step or each number until the end of the number. What they do is they divide the numbers and then sort them and then rearrange them in the right order. It is much faster, and we have to remember that you can use bubble sort for smaller lists, but for larger lists and for faster sorting, it's always recommended to use merge sort. We do have much other better sorting algorithms, but that is out of the scope for key stage 3 and key stage 4 levels. Let's see how the merge sort works. So we have these numbers 6, 5, 3, 1, 8, 7, 2 and 4. We first split them into equal lists. Because we have got 8 numbers, we split them into 4 each. We don't sort them now at this point. We just split them, keep splitting them up. Now, so this is where this divide part of the divide and conquer happens. We again split the 4 into 2 each, sets of 2 each, and then we split the sets of 2 each into sets of 1 each. So now at the end of our divide, we have got each number in its own list. Now that we have got all of them divided, we have to sort them and merge them back and conquer them in the right order. So we take 5 and 6 and then 6 and 5, and then we put them in the right order because we are taking only 2 numbers. We compare only those two and put them in the right order. So from 8 we split them into groups of 4 each, and then we split them into groups of 2 each, and then group of 1 each. Now we are going back the ladder and saying from groups of 1 each we are going to make them groups of 2 each by taking 2 consecutive numbers and then merging them together. So we take 6 and 5, we merge them in the right order by comparing if 6 is less than 5. If it's not, we add 5 first and then add 6 next, and that becomes one group of 2 numbers. Then we take 3 and 1 and then make a group of 2 numbers each in the right order. So it becomes 1 and 3. 8 and 7 become 7 and 8. 2 and 4, they are added as is because they are already in the right order. So from a group of 1 number each, we have got a group of 2 number each. Now from the group of 2 number each, we make a group of 4 number each. So for that, we take 2 consecutive groups of 2's. So 5 is less than 1. We check if it is true. It is not, so we add 1 first. And then we check is 5 is less than 3. No, it is not, so we add 3 next. And now we can add 5 and 6 as is because we know they are in the right order. So we add them to the list. So now we have got 1, 3 and 5 and 6 in the right order. Similarly, we take 7 and 2 and compare. We know 2 is less than 7, so we add 2 first. Then we compare 7 and 4. We know 4 is less, we add 4 to the list. Then we add 7 and 8 to the list. We don't have to compare them. Now, once that we've got a group of 4 each, we just merge them again into a group of 8, which is a final list. the same way that we have done so far. So we take 1 and 2 and see which is the lowest, 1, so we add 1 to the list. And we take 3 and 2, we check which is lowest, it's 2, so we add 2 to the list. Then we check 3 and 4, we know 3 is less, so we add 3 to the list. 5 and 4, 4 to the list. 5 and 7, 5 to the list, and so on until we get the right number. So we have to remember that we always check from the left to the right and then compare if it is lesser and add accordingly. So this way we are not checking every number with every other number. We are checking only in their small groups, and by virtue of them being in the right order in each group, it is easy to merge them back in the right order. So that's why it would take much less time to do a merge sort for a larger list of numbers or records than a bubble sort. You can do the same thing with this. So we split them up into groups of 4 each, split them into groups of 2 each, split them into group of 1 each, and then start adding them back. We check 4 and 8, 2 and 6, 7 and 3 in the right order, 5 and 1 in the right order. Then we make a group of 4 each now in the right order, and then we make a group of 1 at the end. So this is how your merge sort works. So we have split them up and merged them back in. This is a visual representation of how it looks like. So that's pretty much about sorting algorithms so far. Now, in some cases, we also said, for example, if you want to, in the first place in Amazon, if you want to look up for laptops or your gaming consoles or whichever is necessary for the current scenario, you do have to do a search first. Otherwise, you will be there forever looking for what you need. So we need an effective searching algorithm too. And then we can do the sorting. So what are the different types of search algorithms that we have? Again, we have many search algorithms, but for our scope, we are looking at only 2 key ones, which are linear search and binary search. The searching algorithms are not only used for shopping and other external things, they're also used in computational activities because you do search for a lot of records or for files and contents in a file and stuff like that. Let's see how search algorithms work, and especially the 2 types that we have talked about. A linear search is a very simple search algorithm where you have a list of data, it can be numbers or names, and then you search through them one by one until you have found the one that you are looking for. Let's have this list and let's see how we go through the linear search algorithm to look for the number 4. We take the first number and see, is 6 equal to 4? No. So we move on to the next one. Is 5 equal to 4? No, it is not. Is 3 equal to 4? No. Is 1 equal to 4? No. Is 8 equal to 4? No. Is 7 equal to 4? No. Is 2 equal to 4? No. Is 4 equal to 4? Yes. So we have found a number. Sometimes we might have to go through the whole list and not find a number too. The best case scenario in a linear search would be if your number is found in the first item of the list. That means you hit the jackpot, you don't have to search the whole list. The worst case scenario will be if your number is the last element of the list. You would have to go through the whole list to find your number. Imagine if this is going to be a million records or a million list of numbers. It's going to take a long time to find your number. This is something similar to what you would end up doing if you have a list of notebooks in your classroom and you want to see if you want to look up for a particular person's notebook, you have to keep looking at the names on the top of the notebook to see if the notebook belonged to the person that you were looking for, and keep searching until you find them, which is a very tedious process. You can do the same for this linear search activity if you want. So you're looking for the number 42. Is 7 equal to 42? No. Is 14 equal to 42? No. Is 21 equal to 42? And so on and so forth until you find 42. The good part is you don't have to do any more searches after you have found your number. Now, we saw that we have a best case and a worst case scenario for linear search, and you never know what might happen. And it becomes very tedious and time consuming if you have a million numbers or million set of records to search for. So we have another searching algorithm which is called a binary search, which helps you to search in half the time used to do the linear search. It's also called as a half interval search. This works much similar to how you would look up a word in the dictionary. If you wanted to look for a word in a dictionary, like for example, computation, and you open the dictionary in a random location and you end up in page which has a list of words starting with F. Now, you know that because it's in a sorted order, you know that C, which is computation, is found before F. So you would concentrate only on the pages before F. So you again pick a random page from the beginning to where your F was, and then you look up for the word, see which page you landed. If you ended up on page which has the words B, you know that C words are after B, and then you search only for those pages which has B and C words in it. So you kind of restrict the search that you would do because you are not looking for the whole, like you are not looking through the whole dictionary to find your word. You are actually dividing them into small sections and looking up at only those that matter. That is a binary search. Let's see how it works with respect to numbers and what is the algorithm behind it. The key thing for a binary search is that you need a sorted list. So you cannot actually do a binary search if the numbers are not sorted. So we've got a sorted list of number, and let's say we are looking for the number 4 here. What we do is we take the middle number. So we divide 15 by 2 and we pick up the 7th or 8th number depending on how you want to use a 0.5 and then land on the number. So we've got 8 as a dividing point, and then we check if 8 equals 4. No, it is not. Now we know that 4 is less than 8, so that means any number greater than 8 is of no use for us in our search. So we ignore all the numbers from 8 to 15. Now we have limited our search only for numbers from 1 to 7. Now we again land on the middle number in this case, which is 4. Is 4 equal to 4? Yes, it is. So that means we have found a number. So we did not have to actually go through individual number to look for number 4, and we found a number just by 2 search. Let's do another example. We are looking for number 35 in this list, and again we have a sorted list. We have 7, 14, 21, 28, 35, 42, 49, 56, 63, 70 and 77. So the middle number we are looking for is 42. Is 35 less than 42? Yes. So that means we ignore all the number 42 and above because 35 is not equal to 42 either. So we remove all those, and now we find the middle number for this, 21. Is 35 less than 21? No, it isn't. So that means we don't need any number less than or equal to 21. So we ignore that. Now we have got 2. So we pick any number among these. So let's say 2 divided by 2 is 1. So we have 28. We know that 28 is not equal to 35. So we ignored that number and we are landed with only 35, which is our number, and we have found it. So we have found that in 4 searches, even though we had around 1, 2, 3, around 11 numbers, we could find our number in 4 search. Now, in this case, we were able to see those numbers, but how does a computer work it out? Because it doesn't have eyes to see it. So it can be, so all the numbers are hidden in a memory location, so it doesn't know what contains what. So let's look for the number 73 in the sorted list via binary search. Okay, if we don't know what numbers are there, and all we know is that it is sorted. So let's pick up the center. 5. Oh, okay. So 5 is a middle element, and we check if 5 is less than 73. Or where would 5 be? Okay, so it is less than, so we have to look for numbers greater than 5. So we ignore all the ones that are to the left of 5, and 5 is not equal to 73 either. So we ignore all the ones that are in red. Among the ones in green, it checks again, takes the middle one and checks. It's 13. Is 13 equal to 73? No. But is 13 greater than 73? No. So that means we have to ignore everything which is less than 13. So we ignore the 13 and the one left to it. We've got only 2 left. It finds the first one. It's 21. Is 21 equal to 73? No, it isn't. So that means, and 73 is greater than 21. So it checks only the ones on the right. And it checks if 73 is equal to 34. No, it isn't. Sadly, it has not actually found the number that it was looking for. So, and it has exhausted the whole list. So we have searched the entire list and we haven't found 73, and it concludes that it is not there in the list. So all it took for it was only 3 or 4 searches to know that the number was not there in the list, instead of going through all the 9 elements in the list to find out if it was there. So you reduce the number of searches that you would do, or a computer would do, to look for a number, and it ensures that the search is done faster. And this is a very good searching algorithm to use on a large set of data, and is widely used too. So that's the end of this video, where we have seen the examples of algorithms which are commonly and widely used, which is sorting and a searching algorithm. And the best ones among those that we have looked for today is the binary search, which is a better search than the linear search, and the merge sort, which is much better than the bubble sort.